We have arrived at a version of the Navier-Stokes. We have cheated. We have used the Eddy viscosity hypothesis and gotten rid of 6 unknown functions, but we still have 2 unknown functions left that we have to sort of decide what to do. First of all, look at the pressure inside this equation now. It reads pressure over density. If you look into the cases you have run so far in the open foam, everybody has been incompressible. And if you look at the density, sorry, not the density, the dimensions of the pressure, it is not Newton per square meters as you are used to. What open foam actually is calculating is pressure divided by density. So that's a surprise for you. So if you want the real answer to be in Pascal for the pressure, you have to multiply with a given any density for a given problem. So the one we have done so far, Pitts-Daly, square cavity, dam break, and so on, everybody has been with a constant density which doesn't appear anywhere in the equations. So you solve this quantity and call it pressure. Okay? Now let us construct a very simple turbulence model. I say that I forget about this K. I mean, I know he's there, turbulent kinetic energy, but I just call this square bracket, that's my pressure. Because I'm not interested in him, actually. I'm not interested in the pressure even. So I just call this entire square bracket as the unknown pressure. Then I'm left with one single unknown function, viscosity. And one turbulence model is called Spalard-Almaraz. It's just based on one function, one unknown function. So you have one separate transport equation for this quantity alone. That is one turbulence model that we are going to look into. Very simple indeed. Just one single unknown function. But inside this family of turbulence models, the simplest one, that was a zero equation. No transport equation, except the Navier-Stokes, of course, but no transport of any turbulent quantity. So there you will then use just some algebraic equation for this guy, like Prandtl's mixing layer, is the most famous one. Actually works, but only for very simple problems. Then you had one equation problems. Then you needed one quantity that can move, typically the Eddy viscosity. Also, you have one equation models for K that exists. Then you need another equation to couple these two functions together. Just an algebraic equation. More interesting will be the family which we call the 2 equation models. That's where we find K epsilon, K omega, the most important turbulence models that we are going to use. Here in the book by Versteeg, he describes how you can sort of do some manipulation here with the Navier-Stokes, the Reynolds average Navier-Stokes, multiply with one velocity component, do a lot of algebra. You can find here a transport equation, sort of a version of the Navier-Stokes, that describes the transport of big K. This is the total of the mean turbulent kinetic energy. If you subtract that one from the Navier-Stokes, you will actually end up with this one. This is a transport equation of the quantity K, the turbulent kinetic energy. So here you have the correct analytical expression for transport of K. And if you look into that equation a little bit in detail, you will be rather scared. I mean, if K is an unknown function, describe him, find him. The 2 first terms here, they are quite okay. You have here the rate of change of the quantity, time derivative, and then advective or convective acceleration terms. But then you have a whole bunch of nasty terms on the other side. What's this one? Here's the pressure fluctuating multiplied with a velocity fluctuating, and then time averaged. Thank you very much. What are this? And you can't really go in the lab and measure these quantities. How do you measure pressure and velocity in the same point at the same time? That's not possible. At least nobody has done it yet. And here, a very complex, and here very complex. These small s's, if you can recall that one, the cross derivatives, and then time average. Awful, terrible, forget it. You can't really solve this one analytically, no way. It's a whole, way too many unknowns. But if you look at the terms on the right hand side, you will have here all these terms. They will have a derivative in front of them. Derivative in front that we call a diffusion term, diffusion mechanisms. So you will write a transport equation for K. You can do it like this. Time derivative equals whether you want the density in there or not, that's up to you. So here I would call all these three terms here a diffusion term. So I just write diffusion. Then I have here a term that has a viscosity in front. Viscosity in front, that I will call dissipation. That's something that's going to destroy K. Diffusion, he can reorganize the quantity inside a given volume. What destroys him? Clearly something to do with viscosity. He will damp down the kinetic motion. So this one I will call an epsilon, dissipation. The last term is actually negative here, but this guy is going to be mostly negative in a real case. So he will actually be a production term. You might say everything else that has not a derivative in front nor a viscosity, call it production. Simple. So this you can sort of start with this equation instead of this one. Because this, we have no way to calculate these terms correctly. Just forget it. We could just as well have started with this equation. Except the last term, this one we can play around with. This one we can get an exact expression for. Here you have the Reynolds stresses. So there you could use the eddy viscosity hypothesis to substitute here for using the eddy viscosity and so on. So the production term, we can have that one fairly correct. But these two terms, forget it. You have to model them. You don't have any option here to find these terms correctly. No way. No way. This one, it will actually look something like this. Let's see, it will be eddy viscosity multiplied with the large Sij multiplied with dui dxj. So he will not involve any new unknowns. This one was unknown already. So that's one way to construct a transport equation. How to model this one? That's a heavy job, and that one we have to find depending on what kind of turbulence models we will use. Now you can do the same here with not the diffusion term, diffusion should actually be K, like this. Diffusion of K, production of K. This guy, the dissipation, it's a terrible, terrible term. So you can just forget to find him from him, the analytical expression. But you just write another transport equation for the dissipation. Transport equation for epsilon. Well, he will read exactly the same derivative, total derivative equals. You will have a diffusion of epsilon. And then actually, this is strange, you will have a dissipation of the dissipation, something that destroys epsilon. So that's what that should be. Physically, I really can't imagine. Finally, you will have a production of epsilon. So you have the exact same philosophy, a transport equation. And these terms, all of them, has to be modeled. Because I think I brought it with me, I can show it to you. The exact equation, transport equation of the dissipation. It looks something like this. And here you have a derivative in front. So this is a diffusion term. And then you have the viscosity in front here for a couple of terms. Should then be dissipation, and then finally a production term. And of course, they are getting more and more complex. Just forget it. You can't model these out of these analytical expressions. So it's possible to find these equations. Yes, you just have to manipulate with the Navier-Stokes, the real one minus the Reynolds average, multiply with the velocity, yada, yada, yada. A lot of algebra. But yes, it's possible to find these equations exactly. But it doesn't help you. Just forget it. So throw it away, and you jump to this one directly instead. Much better. So how they are modeled. You find a short description here in the Versteg book, and also in the turbulent notes that you have been given. You still are missing something here. So transport for K, transport for epsilon. You are talking a two-equation model, the K epsilon. But we are not done. Remember, inside the Navier-Stokes, what did we have? Well, we had the K, and we had the eddy viscosity. We didn't have any epsilon. So something is missing here. Of course, you need the epsilon because he enters into the K equation. But so nobody has told us now what to do with the eddy viscosity. And for short, the coupling is given by Prantl Kolmogorov. Also based on dimensional analysis, you find that eddy viscosity is given by a constant multiplied with K square over epsilon. For short. And then we're done. Then we have two transport equations. We have for K and for epsilon. And we have one algebraic equation giving us the eddy viscosity that is entering into the Navier-Stokes. So now we have a closure of all the equations. But. Let's see here. Here you have the standard K epsilon model. Transport equation for K. Here the diffusion term has been modeled. The dissipation term, that's just the dissipation directly. And here the production term. And you see this one is not modeled. There you have the eddy viscosity. So this is the correct term as you have it in the analytical expression for the transport equation. But these two are modeled. And the transport equation for epsilon, looking something like this, here everything is modeled. Nothing is taken from the analytical equations because they are useless. So a diffusion term, and you will have a production term and a dissipation term. What is bad with the model, if you look at it a little bit, here you divide by epsilon. Here you divide by k, and here you divide by k. So what the heck is going to happen if you simulate something that is turbulent, but all of a sudden down here in the corner the flow becomes laminar? That's a very bad idea. Because in a laminar flow, k is 0. He is exploding. Epsilon is 0, he's exploding. So k epsilon, he can't handle laminar flow. I mean, it's here. Of course, all codes will cheat. So they don't divide by epsilon. Oh no. They divide by epsilon plus, and then we have 10 to the very small number. Shh, don't talk about it. Of course they do. And of course they do it here as well. Or else he will very rapidly explode. Not to mention, if they become negative, then also instant explosion. So yes, you will have some safeguards in your code, because finding a solution you will typically have to iterate a little bit. So it's a little try and fail with different solutions. And during an iteration process, they might become 0 or even negative. So yes, they use a lot of these dirty tricks in the programming, or else you would never, ever find a solution. This was k epsilon. Any questions so far? So you have the Navier-Stokes plus 2 additional transport equations. So it's a little bit expensive, of course, with regards to CPU, and it's a high Reynolds number model. Should be very high because of this not happy with laminar flow. So for low Reynolds number problems, still turbulent, but fairly low Reynolds number, you shouldn't use the standard k epsilon. Then you have special models with low Reynolds numbers. In Versteeg, after each model, he has a quite nice description of the different models, then what you need, where the models are good and where the models are bad. So should be listed here somewhere. No, well, it comes later. Here, by the way, is the other one, the Spallard-Almaraz turbulence model. That was just transport of the eddy viscosity model, just one transport equation model, looking something like this. Also, a lot of modeling, of course, on the other side there. The K omega model, very popular, just as good as the K epsilon, and in many instances actually a lot better. So the sad thing was that the K epsilon was sort of the first 2 equation model, quite advanced model, that actually succeeded. So a lot of people used that one from then on, and we have a lot of reference material with K epsilon. K omega came later, so it's not that well investigated, but in many cases it's a much better model. Omega here being sort of a turbulent frequency, but else it's fairly close philosophy as to the K epsilon. You don't use the epsilon equation, then you use an omega equation instead. We will have more information how to use these models in open form later on. SST K omega, that's actually quite interesting. You have a mix between K epsilon and K omega. So you use the models where they are good, and you use the other models where they are bad. So it's a hybrid scheme, quite advanced.
You mentioned that one model is better than the other.
Yeah.
What is then the definition of better? Does it mean represents reality better, or is it faster for CPU?
No, it describes the reality better. Yeah, that's what I would call a good model.
Okay.
So a very good model is if it's very simple and still can describe the reality, and that's the best model. So sadly, to describe the reality, you have to use quite complex models if your reality is complex.
Yeah. And how is that on CPU power, more or less?
K omega, K epsilon, fairly equal here. There is an issue with resolving the boundary layer close to walls. That is a headache which we are going to address then on Thursday morning, because that's important. And also how this is done in open form. Sometimes you have to resolve it, expensive. Sometimes you actually have to avoid it. That's actually very nice. We'll see also this in exercise 4. So we'll come back to this issue because it's important. Oh yeah. What I wanted to find was this nice list. ASM. Should be more lists here. K epsilon. Standard K epsilon. Advantages: simple, nice performance for many industrial relevant flows, well established, the most widely validated turbulence model. So that's the whole point with using K epsilon. If you have a problem, then you can find on the internet a problem close to your, sort of the same Reynolds number range, the same roughly the same geometry, or at least the same family of geometry. Then you can find some reference results. People have definitely tried this before with K epsilon, and then you can tell, was it a good idea or a bad idea with K epsilon for my problem. We know it's quite poor for flows where you have, say, curved boundary layers, a lot of swirls, rotating flows, where you have strongly influence of anisotropy of the Reynolds stresses, or say the turbulence quantities. Remember, for the K epsilon and K omega for that matter, they have no sense of direction. K, that's the kinetic energy, 1/2 velocity squared. And velocity squared, then the directions are lost. So he's blind for direction, meaning he's sort of based on that the turbulence is isotropic. So if you look in this direction or in this direction, you see sort of the same turbulence structure either way, which is in some cases a big lie. So he can't describe everything, no, especially when you have a large elements of anisotropy. So what do we do if we don't have a good solution with K omega or K epsilon? Well, we go to the next level. This is the most advanced level, at least that you will hear about, in this Rans family, a full Reynolds stress model. Reynolds stress model. RSM. Now be careful, because I know a lot of commercial codes, they claim they are using an RSM model and they are lying, they are not. So a full Reynolds stress model, that is, you need transport equations, not for K and not for epsilon and not for the Eddy viscosity. We don't use the Eddy viscosity hypothesis whatsoever. We are back to the original Rans. Let's see where we have it. No, I didn't have it. Ah, never mind. Here I had inserted the eddy viscosity hypothesis. If you don't do it, then you will have the Reynolds stresses there. So what we want to do now is have full transport equations for all Reynolds stresses. For all Reynolds stresses. So now you are talking ddt of then u fluct I, u fluct j, time averaged. This one. And again, yes, we can go to the algebra, manipulate with Navier-Stokes, and actually find the analytical correct equation for this transport equation for any of these 6 unknown functions. Yes, we can do that, but why should we? I can show you the equation. It starts here, and then it continues all the way down here. So again, forget it. This is the correct analytical transport equations. No way you can deal with this, except the first one. This one is analytical. Remember, u fluct, they are already unknown. These are the Reynolds stresses. And here just multiplied with the average velocity gradients. Again, already unknown. So the production term, this we have exactly, analytical expression. The rest you can forget. No way you can handle this. Pressure fluctuate, multiplied with the velocity. Triple correlations, forget it. This is very, very hard to find correct. But when we look at all these terms, we will have sort of the same stencil, the same layout of a transport equation. You will have a production term, you will have a diffusion term, you will have a dissipation term, and then we have something new. We have something called phi ij. This term is actually with pressure fluctuating multiplied with this gradient of the fluctuating part. We call it phi, and that is a new term. This one now called pressure strain. Pressure strain, that is what it physically is. If you look at the analytical equation for it, pressure fluctuating multiplied with the strain. What it actually do is redistribution, because remember, the Reynolds stress is a tensor. It's a 3x3 matrix, but it's symmetric, so 6 unknown functions here. And this redistribution, he can take energy from one of these components and give him to some of the others. So he is a redistribution of energy among the unknown functions. And clearly now we have gotten a sense of direction. Opposite to the k epsilon, k omega 2 equation models, which have no sense of direction whatsoever. But here you will have components for each direction, u square, v square, and so on. So this model, much more advanced. Oh yes, and can cover much more physics. But the price you pay is the models. I mean, as you can see, very, very complex. Yes, we have to model all these terms. The epsilon, actually, the dissipation, it's typically modeled stealing the transport equation from the K epsilon equation. So we use this one. Actually, it should be in 1 epsilon for each of the different 6 functions, but you use the same for all of them. Here we are doing so much error anyway, so another error hardly matters. So remember, modeling, you have to think a little bit pragmatic. So model, model, model. Of course, they have to be modeled. And these models are getting quite complex. There's a lot of physics they should cover. So a full Reynolds stress model will typically involve 20 to 25 constants that you have to play around with. You have to find a set of constants suitable for your problem. That can be hard to find. For the K epsilon model, you have 3 or 4 constants you can play around with, and they are typically universal. A little bit change from one problem to the next, but normally you don't mess with them. But the more advanced the model, the more constants, parameters entering into the model, harder to use, of course. And now also, what's the price? For a full Reynolds stress model, you need 6 transport equations for these Reynolds stresses, plus 1 transport equation for the dissipation, plus you have already had 3 transport equations in the Navier-Stokes, 1 for each velocity component. So a total of 10 transport equations. This is getting expensive when it comes to CPU. But it covers more physics, absolutely. So this is what we call a full Reynolds stress model. Okay, any questions to that one? I don't think we have the option in OpenFOAM with a full RSM. I don't think so. I'll check a little bit further, but I don't think so. So it's, you see, it's very hard to use a full Reynolds stress model. The last one we are addressing today it's a sort of a little bit cheating. It's a model that lies between the 2 equation family and the full Reynolds stress model. It's called an ASM. ASM stands for Algebraic Reynolds model. ASM. So with this model, you start with K epsilon. Start with K epsilon, and you have obtained a solution there. Then you use algebraic equations for the Reynolds stresses. So then you will have an equation saying Ui, Uj, flux time averaged equals, and then just algebraic equations involving K and epsilon. I'm not sure if we have an example for such equations. Zero. I believe they should be here somewhere. Must be further down here. No, not here. I guess he stopped at K epsilon. Oh, he doesn't have it. Okay, never mind. The equations are just pure algebraic equations, no derivatives, no transport equation at all. Very simple actually, so it's a very cheap way. First find a solution to K epsilon, then you switch on the algebraic stress model. Just to see, will this influence my solution? And if you have a problem where we know that K epsilon has problems, like a big swirl or a rotating flow or a curved channel or something, you should just switch on an ASM. That's very cheap, and then he should cover much more of the physics, more correct. So an ASM is really something that is recommended. And there, a lot of the different commercial codes, when they claim to be using a Reynolds stress model, they actually mean an algebraic stress model. So they cheat. A full Reynolds stress model, way more advanced. So this ASM, sort of a very cheap and simple way towards a full Reynolds stress model. But it is not a full Reynolds stress model. Yeah. Large eddy and DNS, we spoke a little bit about last time. So that's nothing that you are going to play around with, I hope. The project, that's a little bit up to you, of course, but I won't recommend this. It's very heavy simulations. You need a supercomputer in general, so be careful. Of course, it could be fun if some of you wanted to test it a little bit with a very simple flow that you can do on a laptop and see how they perform. So looking into the world of possible projects, think of the project as a test of the open foam. How does he perform? What will happen if I use a DNS but I only do it in 2 dimensions? See what happens. That could be interesting. So it's up to you actually what kind of project you want to do. So don't be frightened with doing something that should be impossible and should be a very bad idea. It's just a test anyway. So you're allowed to actually do whatever you want. But I won't go through the details with LAS and DNS. It's a little bit out, I would say, for this course. Although we know in OpenFOAM we have some models, some codes that can handle it. That will then be the topic on Thursday morning. A little bit more in detail how we use these models in OpenFOAM. Okay? So tomorrow, exercise, guidance for exercise 3 and exercise 1 and 2 if you still are fighting with those, that's okay. And also if you are fighting with OpenFOAM. Any questions? Then we stop here.